All right, 5.2, exploring quotients of polynomial functions. The quotient of two polynomial functions results in a rational function which often has one or more discontinuities. Okay, so we're looking at here at different types of areas where a function can be discontinuous. In the previous units, we've talked about asymptotes, or some sort of hole happening. So and that's exactly what we're looking at in this unit, is we're going to look at different discontinuities and why they exist. So a rational function, let's say a function with a polynomial in the numerator and a polynomial in the denominator, has a hole at x equals a if we plug it in and it equals 0 over 0. This occurs when p of x and q of x contain a common factor, i.e., it gets canceled when you're simplifying. So here's an example of that. F at x is equal to x squared minus 4 and x minus over x minus 2. Why does this graph look like the following example? So let's just look at it in a larger version of this graph. Okay, we're going to do that next. Here it is. Why is that the case? Well, let's look at the beginning of this and let's start that again. All right, so here's our graph, and our graph it looks like this, and there's a hole. If you look really carefully, there's a hole right about here at, funny enough, x equals 2. Why is there a hole there? Well, looking at this function, we know there's a restriction. The restriction on this function is x equals 2. When I factor the numerator, I get x minus 2 times x plus 2 over x minus 2 on the bottom. So before we can cancel, we need to state the restriction. So we put that in a box above the actual function. And we say, okay, provided that x does not equal 2, I can cancel. How am I going to cancel? Well, the x minus 2 in both the top and the bottom get canceled, so that you get a final result of x plus 2. What is x plus 2? Well, x plus 2, folks, is a line. This is the line for x plus 2. Except at x equals 2, because it got canceled, it was originally a restriction, it remains a restriction. That means at 2, there has to be a hole there, because at that value, the function does not exist. Because remember, it wasn't a line to begin with, it became a line after we simplified it. All right, next one. A rational function, f at x, with a polynomial over a polynomial, has a vertical asymptote at x equals a if, by plugging in the value, you get a number on the top and a 0 on the bottom. What that means is that it is a true restriction that doesn't get simplified. So here's an example of where there is a vertical asymptote at x equals 2. Okay, so for this function, let's just make this function a little bit larger so you can see it. And we can see it, and you can see what happens. So here it comes larger. You'll notice that at x equals 2, right here, there is a vertical asymptote. That vertical asymptote has a very important feature, and that's because the denominator did not get canceled. There is another asymptote going this way, which we'll talk about in a second, known as a horizontal asymptote. But right now, we're just focusing on the vertical asymptote. All right, let's keep going. So rational function f at x equals p over qx has a horizontal asymptote only when the degree of the numerator is less than or equal to the degree of the denominator. So, an example of that is this one here. In this case, both the top and the bottom have the same degree. So, the horizontal asymptote occurs as if you were doing a long division. Another way to do it is to understand that both of these have the same degree. So when I take 2x and I divide it by x, just the highest power coefficients, we end up with a value of 2. But that's not the important part, folks. I want you to focus on the actual graph itself. So let's look at the graph so that you can see this graph on a larger scale. So just 1 second. Let me enlarge it for you, okay? And we enlarge it so you can look at the actual graph. If you look at the graph, you can see here that there is a vertical asymptote at x equals -1, and there's a horizontal asymptote at 2. All right, and that again is because we look at these values and say, okay, how does this reduce? If we were to use long division, we would find that the quotient is actually 2 itself. All right, let's go to the next problem. A rational function, f at x over qx, has an oblique asymptote, known as a slant asymptote, only when the degree of the numerator is greater than the degree of the denominator by exactly 1. So it's very important that the numerator is greater than the denominator by a degree of 1. We don't go into further degrees in this course or in calculus. So f at x is equal to x squared plus 4 over x plus 1. Let's talk about that for a second. So this numerator cannot be factored. This denominator has a restriction of x cannot equal -1. So that is going to be our vertical asymptote. Let's look at a bigger version of this same graph. There it is. So here's our function right here. This is the function, x squared plus 4 over x plus 1. This right here is the vertical asymptote. Here is the slanted asymptote with this equation. How would one get that equation? Well, folks, that dreaded long division, that's how. So what you would do to find the slant asymptote is you divide the equation, the numerator, by the denominator using long division to find out that the quotient is x minus 1. So the quotient that's up here, folks, that turns out to be the equation of the slant asymptote. All right, next problem. The breaks or discontinuities in a rational function occur when the function is undefined, i.e., when the denominator is 0. So we will have a sort of break in the graph. Now, the values that must be restricted from the domain of the rational function result in key characteristics that define the shape of the graph. That means that if I take all the restrictions would equal either vertical asymptotes or holes on the graph, depending if it cancels or not. The characteristics include vertical asymptotes, which are infinite discontinuities, and holes, which are known as point discontinuities. Holes only exist when a graph has been reduced and it gets rid of one of the restrictions. All right, finally, the end behaviors of many rational functions are determined by either horizontal asymptotes or oblique asymptotes. All right, that's the end of this video, folks. Basically, you have to go through the problems in the textbook and try and figure out what kind of asymptotes they'll have and what the values of those asymptotes will be, the exact equations. All right, then, take care. Have a good night.